Now the next algorithm I'm going to talk about is decision tree. Decision tree is one of my favorite algorithms because it's very simple to understand how a decision tree works. So guys, before this we discussed linear regression, which is a regression algorithm. Then we discussed logistic regression, which is a classification algorithm. Remember, don't get confused just because it has the name logistic regression. Okay, it is a classification algorithm. Now we're discussing decision tree, which is again a classification algorithm. Okay, so what exactly is a decision tree? Now, a decision tree is again a supervised machine learning algorithm which looks like an inverted tree wherein each node represents a predictor variable and the link between the node represents a decision and each leaf node represents an outcome. Now, I know that's a little confusing, so let me make you understand what a decision tree is with the help of an example. Let's say that you hosted a huge party and you want to know how many of your guests are non-vegetarians. So to solve this problem, you can create a simple decision tree. Now, if you look at this figure over here, I've created a decision tree that classifies a guest as either vegetarian or non-vegetarian, right? Our last outcome here is non-veg or veg, right? So here only you understand that this is a classification algorithm because here you're predicting a categorical value. Each node over here represents a predictor variable. So eat chicken is one variable, eat mutton is one variable, seafood is another variable, right? So each node represents a predictor variable that will help you conclude whether or not a guest is a non-vegetarian. Now, as you traverse down the tree, you'll make decisions at each node until you reach the dead end. Okay, that's how it works. So let's say we got a new data point. Now we'll pass it through the decision tree. The first variable is, did the guest eat the chicken? If yes, then he's a non-vegetarian. If no, then you'll pass it to the next variable, which is, did the guest eat mutton? If yes, then he's a non-vegetarian. If no, then you'll pass it to the next variable, which is seafood. If he ate seafood, then he is a non-vegetarian. If no, then he's a vegetarian, right? This is how a decision tree works. It's a very simple algorithm that you can easily understand, right? It is drawn out like this, which is very easy to understand. Now let's understand the structure of a decision tree. I just showed you an example of how the decision tree works. Now let me take the same example and tell you the structure of a decision tree. So first of all, we have something known as the root node. Okay, the root node is the starting point of a decision tree. Here you'll perform the first split and split it into two other nodes or three other nodes depending on your problem statement, right? So the topmost node is known as your root node, right? Now, guys, about the root node is assigned to a variable that is very significant, meaning that that variable is very important in predicting the output. Okay, so you assign a variable that you think is the most significant at the root node. After that, we have something known as internal nodes. So each internal node represents a decision point that eventually leads to the output, right? Internal nodes will have other predictor variables, right? Each of these are nothing but predictor variables. I've just made it into a question. Otherwise, these are just predictor variables, right? Those are internal nodes. Terminal nodes, also known as the leaf node, represent the final class of the output variable. Okay, so these are basically your outcomes, non-veg and vegetarian. Branches are nothing but connections between nodes. Okay, these connections or links between each node is known as a branch and they are represented by arrows. So each branch will have some response to it, either yes or no, true or false, 1 or 0, and so on. Okay, so guys, this is the structure of a decision tree. It's pretty understandable. Now let's move on and we'll understand how the decision tree algorithm works. Now, there are many ways to build a decision tree, but I'll be focusing on something known as the ID3 algorithm. Okay, there's something known as ID3 algorithm. That is one of the ways in which you can build the decision tree. ID3 stands for Iterative Dichotomizer 3 algorithm, which is one of the most effective algorithms used to build a decision tree. All right, it uses the concepts of entropy and information gain in order to build a decision tree. Now, you don't have to know what exactly the ID3 algorithm is, it's just a concept behind building a decision tree. Now, the ID3 algorithm has around 6 defined steps in order to build a decision tree. So, the first step is you will select the best attribute. Now, what do you mean by the best attribute? So attribute is nothing but the predictor variable over here, right? So you'll select the best predictor variable. Let's call it A. After that, you'll assign this A as a decision variable for the root node. Basically, you'll assign this predictor variable A at the root node. Next, what you'll do is for each value of A, you'll build a descendant of the node. Now, these three steps, let's look at it with the previous example. Now, here the best attribute is eat chicken. Okay, this is my best attribute variable over here. So I selected that attribute. And what is the next step? Step 2 is assign that as a decision variable. So I assigned eat chicken as the decision variable at the root node. Now you might be wondering, how do I know which is the best attribute? Right? I'll explain all of that in a while. So what we did is we assigned this at the root node. After that, step number 3 says for each value of A, build a descendant of the node. So for each value of this variable, build a descendant node. So this variable can take two values, yes and no. So for each of these values, I build a descendant node, right? Step number 4, assign classification labels to the leaf node. To your leaf node, I have assigned classification. One is non-veg and the other is veg. That is step number 4. Step number 5 is if data is correctly classified, then you stop at that. However, if it is not, then you keep iterating over the tree and you keep changing the position of the predictor variables in the tree, or you change the root node also in order to get the correct output. So now let me answer this question. What is the best attribute? What do you mean by the best attribute or the best predictor variable? Now, the best attribute is the one that separates the data into different classes most effectively, or it is basically a feature that best splits the data set, right? Now, the next question in your head must be, how do I decide which variable or which feature best splits the data? To do this, there are two important measures, right? There's something known as information gain and there's something known as entropy. Now, guys, in order to understand information gain and entropy, we look at a simple problem statement. This data set represents the speed of a car based on certain parameters. So, our problem statement here is to study the data set and create a decision tree that classifies the speed of a car as either slow or fast. So, our predictor variables here are road type, obstruction, and speed limit, and our response variable or our output variable is speed. So we'll be building a decision tree using these variables in order to predict the speed of a car. Now, like I mentioned earlier, we must first begin by deciding a variable that best splits the data set and assign that particular variable to the root node and repeat the same thing for other nodes as well. All right. So step 1, like we discussed earlier, is to select the best attribute A. Now, how do you know which variable best separates the data? The variable with the highest information gain best divides the data into the desired output classes. First of all, we'll calculate two measures. We'll calculate the entropy and the information gain. Now, this is where I tell you what exactly entropy is and what exactly information gain is. Now, entropy is basically used to measure the impurity or the uncertainty present in the data. Right? It is used to decide how a decision tree can split the data. Information gain, on the other hand, is the most significant measure which is used to build a decision tree. It indicates how much information a particular variable gives us about the final outcome. So information gain is important because it is used to choose a variable that best splits the data at each node for a decision tree. Now the variable with the highest information gain will be used to split the data at the root node. Now in our data set, there are 4 observations, right? So what we're going to do is we'll start by calculating the entropy and information gain for each of the predictor variable. So we're going to start by calculating the information gain and entropy for the road type variable. In our data set, you can see that there are 4 observations, right? There are 4 observations in the road type column, which correspond to the 4 labels in the speed column. So we're going to begin by calculating the information gain of the parent node. The parent node is nothing but the speed of the car node. This is our output variable, correct? It will be used to show whether the speed of the car is slow or fast. So to find out the information gain of the speed of the car variable, we'll go through a couple of steps. Now we know that there are four observations in this parent node, right? There is first we have slow, then again we have slow, fast, and fast. Now, out of these four observations, we have two classes, right? So, two observations belong to the class slow and two observations belong to the class fast. So, that's how you calculate P slow and P fast. P slow is nothing but the fraction of slow outcomes in the parent node, and P fast is a fraction of fast outcomes in the parent node. And the formula to calculate P slow is the number of slow outcomes in the parent node divided by the total number of outcomes. So the number of slow outcomes in the parent node is 2 and the total number of outcomes is 4, right? We have 4 observations in total. So that's how we get P of slow as 0.5. Similarly, for P of fast, you'll calculate the number of fast outcomes divided by the total number of outcomes. So again, 2 by 4, you'll get 0.5. The next thing you'll do is you'll calculate the entropy of this node. So to calculate the entropy, this is the formula. All you have to do is you have to you'll have to substitute the value in this formula, right? So P of slow we're substituting as 0.5. Similarly, P of fast as 0.5. Now when you substitute the value, you'll get a answer of 1, right? So the entropy of your parent node is 1. So after calculating the entropy of the parent node, we'll calculate the information gain of the child node. Now guys, remember that if the information gain of the road type variable is greater than the information gain of all the other predictor variables, only then the root node can be split by using the road type variable. So to calculate the information gain of road type variable, we first need to split the root node by using the road type variable, right? We're just doing this in order to check if the road type variable is giving us maximum information about our data. Okay, so if you notice that a road type has two outcomes, it has two values, either steep or flat, right? Now go back to our data set. So here what you have to notice is whenever the road type is steep, so first what we'll do is we'll check the value of speed that we get when the road type is steep. So first observation, you see that whenever the road type is steep, you're getting a speed of slow. Similarly, in the second observation, when the road type is steep, you'll get a value of slow again. If the road type is flat, you'll get an observation of fast. And again, if it is steep, there is a value of fast, right? So for three steep values, we have slow, slow, and fast. And when the road type is flat, we get an output of fast, right? That's exactly what I've done in this decision tree. So whenever the road type is steep, you'll get slow, slow, or fast. And whenever the road type is flat, you'll get fast, right? Now the entropy of the right hand side is 0. Entropy is nothing but the uncertainty. There's no uncertainty over here because as soon as you see that the road type is flat, your output is fast, right? So there's no uncertainty. But when the road type is steep, you can have any one of the following outcomes. Either your speed will be slow or it can be fast, right? So you'll start by calculating the entropy of both RHS and LHS of the decision tree. So the entropy for the right side child node will be 0, right? Because there's no uncertainty here. Immediately, if you see that the road type is flat, your speed of the car will be fast. Okay, so there's no uncertainty here, and therefore your entropy becomes 0. Now, entropy for the left hand side is you'll again have to calculate the fraction of P slow and the fraction of P fast. So out of three observations, in two observations we have slow. That's why we have 2 by 3 over here. Similarly, for P fast, we have 1 P fast divided by the total number of observations, which are 3. So out of these 3, we have 2 slows and 1 fast, right? When you calculate P slow and P fast, you'll get these two values. And then when you substitute the entropy in this formula, you'll get the entropy as 0.9 for the road type variable, right? I hope you all are understanding this. I'll go through this again. So basically here we are calculating the information gain and entropy for road type variable, right? Whenever you consider road type variable, there are two values, steep and flat. And whenever the value for road type is steep, you'll get any one of these three outcomes. Either you'll get slow, slow, or fast. And when the road type is flat, your outcome will be fast. Now, because there's no uncertainty, whenever the road type is flat, you'll always get an outcome of fast. This means that the entropy here is 0 or the uncertainty value here is 0. But here there is a lot of uncertainty, right? So whenever your road type is steep, your output can either be slow or it can be fast. So finally, you get the entropy as 0.9. So in order to calculate the information gain of the road type variable, you need to calculate the weighted average, right? I'll tell you why. In order to calculate the information gain, you need to know the entropy of the parent, which we calculated as 1, minus the weighted average into the entropy of the children. Okay. So for this formula, you need to calculate all of these values. So first of all, you need to calculate the entropy of the weighted average. Now the total number of outcomes in the parent node we saw were 4. The total number of outcomes in the left child node were 3, and the total number of outcomes in the right child node was 1. Correct? In order to verify this with you, yeah, the total number of outcomes in the parent node are 4, right? 1, 2, 3, and 4. Coming to the child node, which is the road type, the total number of outcomes on the right hand side of the child node is 1, and the total number of outcomes on the left hand side of the child node is 3, right? That's exactly what I've written over here. All right, I hope you all understood these three values. After that, all you have to do is you have to substitute these values in this formula. So when you do that, you will get the entropy of the children with weighted average will be around 0.675. All right. Now just substitute the value in this formula. So if you calculate the information gain of the road type variable, you'll get a value of 0.325. Now, by using the same method, you're going to calculate the information gain for each of the predictor variable, for road type, for obstruction, and for speed limit. Now, when you follow the same method and you calculate the information gain, you'll get these values. Now, what does this information gain for road type equal to 0.325 denote? Now, the value 0.325 for road type denotes that we're getting very little information gain from this road type variable. And for obstruction, we literally have a information gain of 0. Similarly, information gain for speed limit is 1. Now, this is the highest value we've got for information gain. This means that we'll have to use the speed limit variable at our root node in order to split the data set, right? So guys, don't get confused. Whichever variable gives you the maximum information gain, that variable has to be chosen at the root node. So that's why we have the root node as speed limit. So if you've maintained the speed limit, then you're going to go slow. But if you haven't maintained the speed limit, then the speed of your car is going to be fast. All right. Your entropy is literally 0 and your information gain is 1, meaning that you can use this variable at your root node in order to split the data set because speed limit gives you the maximum information gain. So guys, I hope this use case is clear to all of you. To sum everything up, I'll just repeat the entire thing to you all once more. So basically here you were given a problem statement in order to create a decision tree that classifies the speed of a car as either slow or fast, right? So you were given three predictor variables and this was your output variable. Information gain and entropy are basically two measures that are used to decide which variable will be assigned to the root node of a decision tree. Okay. So guys, as soon as you look at the data set, if you compare these two columns, that is speed limit and speed, you'll get an output easily. Meaning that if you're maintaining speed limit, you're going to go slow. But if you aren't maintaining speed limit, you're going to go fast, right? So here itself, you can understand that speed limit has no uncertainty. So every time you've maintained your speed limit, you will be going slow. And every time you're outside your speed limit, you will be going fast. All right. It's as simple as that. So how did you start? So you started by calculating the entropy of the parent node. Okay. You calculated the entropy of the parent node, which came down to 1. Okay. After that, you calculated the information gain of each of the child nodes. In order to calculate the information gain of the child node, you start by calculating the entropy of the right hand side and the left hand side of the decision tree. Okay. Then you calculate the entropy along with the weighted average. You substitute these values in the information gain formula and you get the information gain for each of the predictor variables. So after you get the information gain of each of the predictor variables, you check which variable gives you the maximum information gain and you assign that variable to your root node. It's as simple as that.